I hope you can see me in presentation mode now.
Yes.
Excellent. Right. This title of this webinar is the Global Dynamic Soil Data at 30-meter Resolution, a new data product by OpenLandMap, which is again a project or a data portal by the OpenGeoHub. Welcome once more, and glad you made it. Just trying to change the slides now. So I think you know the housekeeping rules. If you have a question, please use the chat box so that we can see your question later for the Q&A. Please mute your microphone when you're not speaking and raise your hand if you have a question later in the Q&A. If possible, please switch your camera on during the Q&A session. And this meeting is recorded and is being recorded, and we will also share the recording later on our websites. The agenda, yeah, we are a bit behind, so I'll keep this introduction short. As I said, I'll say a few words about GeoLDN, and then I'll hand over to Tom to talk about the global spatiotemporal prediction of soil properties at 30 meter. And we have a bit of time for Q&A. I hope you can stretch your calendar slots a little bit behind 2 p.m. Just a very few words about GeoLDN. GeoLDN is a global network and a partnership of actors around the world. We have a world map here showing some of our key contributors and partners like Conservation International, WOCAT of the University of Bern, CEBAS in China, several strong regional partners in Africa. And this network came to life based on a decision of one of the conferences of the parties of the UNCCD in 2018 to support UNCCD in the implementation of the convention. And that's what we're trying to do. We're trying to build bridges between the EO community, between data providers and projects like OpenGeoHub and the people who make use of these data, be it planners or other data users in countries around the world. And you see some of the countries with whom we worked in the past years. We are very grateful for this opportunity to have a joint webinar with OpenGeoHub. And we're grateful that they made available their technical infrastructure for us, because we are sort of in between websites at the moment, and would have been difficult for us. It's my pleasure to introduce Tom Hengel, who many of you know, I'm sure. Tom is the co-founder and director of OpenGeoHub. That is an independent, non-profit research foundation promoting open source and open data solutions. Tom has a background in soil mapping and geoinformation science with a PhD from ITC and Wageningen University and postdoc positions at JRC and Amsterdam University. And he has more than 20 years of experience as an environmental modeler, data scientist, and spatial analyst. At OpenGeoHub, Tom is responsible for the summer school courses. He leads method development, supervises PhD students, and is also responsible for the development of datasets and the provision of technical support. OpenGeoHub has a number of really impressive projects and services like the OpenLandMap data portal, and it's my pleasure to introduce Tom to you. Please, Tom, say a few words more about yourself and the OpenGeoHub, and yeah, hand over to you for the presentation. And really excited to hear about the new data set you're going to talk about for soil monitoring. Over to you.
Thank you, Ben. I will try to share my screen. I hope you see my screen.
You do?
Yes?
Yes.
Okay. So yes, I will talk about the OpenLandMap-soil DB. I made a list of things to discuss. Want to first touch a bit on what is digital soil mapping, why it's important, and then also within the LDN program, and then OpenLandMap, which is not only about soil mapping, but it's about basically building multiple biophysical indices for the world, making them consistent. And then OpenLandMap-soil, how to access data. I'll do a little demo. And then how to report an issue. This research I'm showing you, it's been part of the multiple projects, mainly. Most important to mention, OpenNet Monitor project, Horizon Europe project. Also, Bezos Earth Fund funding the Land Carbon Lab helped us build this data. And Africa Soil, AI for Soil Health project, also Horizon project. But we also build up on products from other groups. Most importantly, we build up on the training data from different organizations. About 7 or 8 organizations contributed about 80% of training data. So most importantly, USDA, Africa Soil Information Services, now at ISDA. Then Lucas soil data from the European Soil Data Center, ISRIC. World Soil Information also compiling a lot of data. So just to mention a few of the organizations. There's a publication about this work. So for those of you who are interested, there's a preprint, but preprint is still in review. So there will be changes, and most likely we will also recompute some of the data. So basically the whole thing I'm showing, it's quite under construction. So you should only use it for testing purposes. It's not for the operational purposes yet. Also very interesting to notice that I started, doing first global soil mapping back in 2009. I just started with 10 kilometers. I made a soil carbon map, and it's I use it just for teaching, just to show how you can do, for example, I can make a soil carbon map of the world, and it is in my book, A Practical Guide to Geostatistical Mapping. About the same time, the Global Soil Map Net project's been initiated, about 2008, 2009. As you see, this paper is from 2009. It was really international coalition, and they kind of predicted, led by Pedro Sanchez, and they wanted 100-meter resolution soil property maps of world. And they thought it's going to take only a few years. But now we're in 2025, and we only managed to produce really high resolution data, so almost 15 years after. So it took quite a history to come to something like which is high resolution. There's also an excellent review of the global soil mapping initiatives by Chen et al. And you can see in that review that you can see which are the most interesting soil properties when you talk about global data. So soil organic carbon, soil organic matter, they stick out, so they're absolute outlier. Then after that is the physical soil properties, special clay, and then clay sand. Then we have pH, bulk density, available water capacity. So this is kind of based on the literature what comes up as of interest. And also you can see the depth of the mapping soil. Lots of studies focus only on the topsoil, so up to 0 to 30 centimeter. But then also there are some studies where this goes to 1 meter and then 2 meter. Typically, soil is defined as 0 to 200 centimeter. So within the LDN program, I know you, which I really like, by the way, LDN program. I like it because it's very practical. It is focuses on really fundamental indices. So the changes in land cover and productivity of land. Then it is very important in LDN. It's important to analyze things through time, so to see whether there are changes. And then you have, as the third indicator, you have the above and below ground biomass, and below ground biomass is practically soil organic carbon. And that's what I'm going to show you now, how we managed to map it, and I will show you also in a demo how to access that. And we were able to do this 30-meter resolution dynamic soil mapping because we put about 3 years of effort to process the Landsat, because Landsat is still the most fundamental, most important open Earth observation data source to do any type of monitoring of environment. And so we put some 3 years of effort, especially last year, to process Landsat, because Landsat, it's raw images. They have clouds, they have snow, and they come only as scenes. So what we did, we computed and prepared mosaics, which are complete and consistent. So you see there's no lines and there's no artifacts. And these are the 30-meter resolution. So we computed them, and we at the moment we only have a bi-monthly, but we're working on a monthly product. And we focused on the years 2000 to 2024. This data has been just published on Copernicus Data Space Ecosystem. It's about 150 terabytes of data. So it's a publicly available under open data license. Once we had these Landsat bands, so about 150 terabytes of data, then several products came out of that. So one of them is the bi-monthly GPP. There's a publication, you can read about it. It looks something like this. So for different bi-months, so 6 images per year, you can zoom in at 30 meter and you can see estimate of gross primary productivity in a gram carbon per square meter per day. And so we're also quite proud of that. And this data is also publicly available. In parallel, we also looked at the terrain modeling. So there are several terrain data sets, and there's lots of LiDAR, space-based LiDAR data sets like ISAT. And we integrated all that, and we produced also an ensemble terrain model of the world. And we produced something 15 variables, so including hydrological indices and morphological indices. And as a byproduct, we also produce median vegetation height maps annual for 2024, also publicly available. All this data is at 30-meter resolution. And all this data, it's relatively large, but it's provided through S3 as Cloud Open GeoTIFF, so you can just drag and drop it into QGIS and you can work with that. This is just example of median vegetation height. This is an area in Brazil, as you see here on the green dot. So this is somewhere in Brazil in this Cerrado region. You can see there's quite some changes over years. There's a lot of conversion of land to pasture land, etc. Everything which you see darker, it's forest, and then these are then often converted to pasture land. But so you can track all that, and then you can see also the trends for every pixel. And then once we had all these things, then we said, okay, let's also do soil properties, and we created a very generic framework which is fully optimized. It's running on our server infrastructure. It's actually it's implemented in C++, because that's the only way we can produce 30-meter resolution space-time predictions. So this is a general scheme that explains how this is running. And you can see we have a compilation of points, which is about 250,000 points with soil organic carbon density, about 400,000 points with soil carbon content, and about 350,000 with soil pH. And here below you see also the soil type. So this is the density of training points. So you can see them for the area. And then what we do a space-time overlay. We use these multi-scale DTM variables from the publication I'll show you. We also use the Landsat-based variables, including the GPP. And we have also climatic variables, including MODIS, land surface temperature, water vapor. So something about 600 layers to start with. And then we do a space-time overlay. We do model fine-tuning. And then we produce the final model that we can then generate predictions we run them 30 by 30 kilometer tiles, which is about 30 by 30 kilometer tiles, and then we can compute everything. And this computing, the modeling, it's quite fast, so it's done in few hours, I think. All variables in few hours. Then the prediction is very costly, so this can take up to 1 week computing non-stop. So it's quite intense, because we also produce the uncertainty, and uncertainty triples the computing time or quadruples the computing time. So that's the output, and we started by testing this EO soil mapper, the framework. We started testing in Europe, and so for Europe we also have a soil health data cube. And then we produced first we did the Europe, and we said, okay, that works. And then we adjusted this to produce the global predictions. So we have both now continental and global predictions, which are basically based on the same framework, but different training data, different covariate data. And I did most of work I did together with my colleagues David and Shumong. So I was leading the preparation of point data and designing the whole thing, and Shumong was optimized the models, and she ran everything in scikit-map. And then Davide was crucial for production to convert this into operational framework so we can produce data. But we also got a lot of help from our colleagues here mentioned. Also, we are very grateful to Travis Neumann for helping us, especially with harmonizing the data. Most of data, it's from USDA and USGS actually training data. So it was very important to zoom into this data and to try to solve that. Also, a big thanks to Jose Luca Safanelli, with whom we also produced this open source spectral library for the world. So he also helped with preparing this data and running the models. The models, they have a limited accuracy, of course. Soil mapping remains complex, even though we have a lot of data and we're doing high performance computing. So we discovered that there is quite still some uncertainty. This is the cross-validation result for the soil carbon density. And so we see we have a limited accuracy, and so this accuracy allows us to detect only, so this is accuracy versus detection limit. And so you can see, because we are somewhere here at the moment, we can detect, for example, effects of deforestation, but we cannot detect on a scale of 5-year effects of carbon sequestration. Most likely, it's we need to go look at for example, 15 years, and then we should be able to detect also the effects of carbon sequestration. So, for example, conversion from cropland to grassland. This is how it looks like. It's a dynamic data set. I will also do a demo. This is Indonesia. You can see areas where you have actually high soil organic carbon density, so tropical peatlands, and you can see how we predict that they're actually disappearing in some areas, which is mainly due to urbanization and deforestation and conversion of land to plantations. And also we use this multi-scale variable, so that's integrated with these spectral indices, and we think also it's help us represent these soil forming processes that happen in different scales. So that's, I think, also improvement from the previous models. These are the accuracy plots for multiple soil properties, so soil carbon density, soil carbon content, pH, and you can see that we run 3 types of comparisons, accuracy assessment. We do stratified testing, so just a single test. Then we do a spatial cross-validation with ensuring that the cross-validation data is distant from the training data, at least 100 kilometers. And then this one is a temporal cross-validation. This is predicting the years which are not used for the training. So the true accuracy is probably very strict accuracy. It's somewhere in between this accuracy and this accuracy. This one is a bit more optimistic. This one is more pessimistic. So the true accuracy will be somewhere in between. And we provide the RMSC in the original space. In the log space, we also provide the D-square, a measure for non-normal variables, and we provide the CCC. So they're all documented. Very interesting discovery is that the GPP comes up. So all this effort we put to prepare this Landsat data, it's paid off because the GPP and NDVI, which are also highly correlated, they come very high for the soil carbon density, soil carbon content. For the pH, we see that it's the salinity grade important as expected, which is determined from satellite images, and then also tillage index, karst, so geological, lithological background, also important for pH, but for soil carbon density, it's practically GPP and then also some climatic variables, primarily precipitation, the bioclim 5. So that's very interesting to see, and it's kind of, I tell people now we have a scientific proof that the GPP explains the carbon. And so if somebody wants to reverse that, say we would like to increase our soil organic carbon, we have a scientific proof that the way to go is to improve your GPP on a scale of 5 to 15 years. And so that will be for me the best recommendation if people are interested. And then also we noticed that this land degradation, it does lead also to loss of soil organic carbon. It's continuously visible, and so you can also explore it in the app. So you can see, seeing the deforestation effects in the world on soil carbon. They are visible, not everywhere. They're not always one-to-one correlation. But in tropical peatland, especially in mangroves, it's visible that there is a loss of soil organic carbon because of deforestation primarily. And then also, as I said, for pH, also interesting to see that it matches the knowledge. So our result of modeling, they match really the knowledge, the soil knowledge of distribution of pH. Okay, with this thing, I think I will now go and do a demo of the app. You still see my screen, I hope. Do you see the app?
Yes, we do. We see world.soils.app in your browser.
Yes. Okay. So when you land on the page, I mean, you have just general information. Then I click on the Explore SoilDB, and so what you see here is now the app. So all these layers are exposed, so you can zoom in and zoom out, and you can see it's a space-time data set, so you can see the changes in soil carbon through time. I would just jump somewhere where it's most interesting. So here's an area in Brazil where there's been let's say, a lot of conversion of land through past. So I can play a bit with the transparency, and so you see there's been a conversion. So if I scroll through time, I can notice maybe some area I can find where there's been a change in soil carbon. One way to do it also is to do a comparison. So now I can compare the recent year and the beginning year. So you see if I go scroll left and right, it allows me to see some areas where there's been a change in carbon. Let's go zoom in here. So let me see, zoom. So I notice, for example, here. So this is most likely there's a urbanization process, as you see. And if I will click now on some location, if I click on any location, it will query the soil carbon density values, and you will see that there is a significant drop, almost 50% drop in soil organic carbon for this area. In general, you can see that the difference is actually between past and current soil carbon are very gentle. So that's also something that we thought it's going to be actually very difficult to map. So I can zoom in also a bit here. And so now we can see these actual farm fields. And again, I see some changes in carbon. This is a more gentle drop in carbon. This is only maybe, my estimate here, maybe like a 10% drop in carbon. So it's a very gentle, you can see it on the images. But it's also most likely because of the conversion of land. I will have to go now look at the past images and see at which year the conversion happened. Also here you can display in this one, I can also display the training points. So those of you who are interested to see whether these points come from, so here are the training points. You see some areas, there's not so many training points. We have still huge gaps, but then also we have here lots of training points. And of course, for US, there's a lot of training points in Mexico. So you can also get an idea about this density of training points. So yeah, that's very quickly the app. Then you can read about the training data, how the training data was prepared and how it was compiled, how you can access the training data. You can also go and visit the GitHub, which shows, so if you look at the GitHub, you can see how to download the data. Easiest thing is to download, to actually open this table and then pick up a layer if you're interested. And then you can just drag and drop that layer. So here's a URL. So you can drag and drop it into the QGIS. And this way you don't have to download, because I think layers are usually about 120 or 140 gigabyte. So that's not so easy to work with. So I will not go and download everything, but you can just drag and drop. Also, there is the stack. If you go to stack, so here you can access both the carbon. So here's the long-term soil organic carbon or different ones. This one is the SolDB. So you can also access here. You have a preview, also one way to access. So there's many ways to access, and there is the one you see, the app. This one is the data is on the Google Earth Engine. So you can load this data directly in Google Earth Engine and do computing, and you can do some assessment. So this is how you can access the data. And as I said, there is also the publication. You can read all about this work and accuracy assessment. You can also see how does this data compare to some previous data products. So you can see here the OpenLandMap. This is the national data set produced for Netherlands, I think. And so you can see the difference, the effect of 30-meter resolution, and this is 250-meter resolution. So you can see there's a lot of detail that you will not get from the 250-meter. So that's how you can access the data, the publication, and if you have any issue, you can report it if you go to the GitHub. So if I open this one, you can report an issue under issues. So if you have some issue, you can just put it here, and then we will try to resolve it and fix the problem as soon as possible. And also, this seminar was relatively short, but I will share with everyone on our OpenGeoHub channel. There is also longer tutorial. I talk about 1 hour 20 minutes, and I'm going through this one here. So I'm going to all these links. I'm going through all these links, and I'm opening things in QGIS, and I'm doing all the modeling and accessing that, etc. So you can also watch that. I will share that with everyone here in the group, so you can access that. And with this thing, I'm open now for questions. Bernd, that was my talk. I apologize one more time to everyone for technical issues. We are now here, so everybody is safe. But I'm open if there's some questions. If there was some questions in QA, I can try to answer. I do see some questions.
Thank you so much, Tom. Yeah, no, thank you very much. That was really fantastic. And thank you also for sharing some links. I think this is a topic which merits some more digging into. I will definitely go through some of the tutorials later, because, I mean, as you all know, mapping soil is not easy. It's quite challenging indeed, because of the high spatial variability and then the temporal issues. And I think it's really impressive to see this work you have done. Yeah, so let's see if we have questions. I hope I see the right.
There was a question about presentation. I just shared it.
Excellent.
Then there's a question about validating the maps. Do we?
I see
yeah.
Need to see the question and answers. Yeah, please go ahead, Tom.
Do we plan to collect new data around the world? So we are not, flying around the world to do soil sampling. It's, it's something you don't even think about. I mean, this is like we're talking. The budget for something like this will be, will have to be enormous. But we can collaborate with countries. So there's more and more data continuously coming up, and so we know, for example, the people collecting soil spectroscopy data. This is very important to eventually to share the data. So there is a whole community, soilspectroscopy.org. So there's a whole community, and this is the way you could share your data, and we will curate this data, and then this data will be plugged into the predictive soil mapping, and this way we also validate our models. As we get more and more data, we always do the reanalysis. At the moment, everything is fully automated, so modeling is now, I mean, it took us a long time to build this. I mean, I'm talking years. It took me almost 13 years to collate this point data. So now it's much easier to do updates, and the key is now just to get more and more people to share the data, and this way we also validate. But I would like to have a project to travel around the world and validate this. So the properties, I don't think it will happen. But I think what could happen is that the countries use this data, and then if they do some national service or something, then they let us know. And there were colleagues from Mexico. They already compare with their data in Mexico, and they posted it. Unfortunately, they didn't get a good match, but I don't know why. So I have to zoom in. But I think that's the way to validate it, that everybody just collects new data and test it and share. Is there a way to add the SOC layer to Google Earth Engine directly as asset without downloading it? Yeah. So the layer is in the Google Earth Engine, and you can read instructions on the GitHub. The instructions how you can load the data from Google Earth Engine. So both the 2-year and the 5-year blocks predictions are available in the Google Earth Engine. Have you mapped available soil salinity and phosphorus? So we are looking now to extend the number of properties. We know that we know what the high priority is the soil carbon, of course, and soil pH, and soil texture fraction. So we knew the sand, silt, clay, and carbon. We did a carbon and carbon density just in case. Now we could add things. It's all dependent on the point data. If we have a point data, if somebody can help us with the point data, we are open to collaborating. This is really open data project. There's absolutely no intention to commercialize at any stage. It will stay CC BY, maybe CC BY share alike. So it will stay really open data. And so if somebody wants to contribute with the point data, we're more than happy to overlay the point data and run predictions. The third shared link, I put that I have a typo.
Yeah, the C is missing, right?
Yes, sorry about that. It's a typo. It's a bit a long-term soil spectroscopy. So here's a one more time. This one I will delete. So that's the soil spectroscopy open source spectra library. Also, we're really proud of making this data available to people, the infrastructure. That's the in situ component. The SoilDB is a global prediction component. The OSSL is an in situ component. And there's a lot of data there already, but there's way more data sitting on people's tables and computers and things. So there's a question by Jacopo Ferrario. Why did you decide 30-meter resolution? Yeah, so 30 meter is because also I think for you and UNCCD and many projects now global layers available at 30 meters, so we wanted to match, especially the land cover products at 30 meter. So we find it very important to match that. And also, as you see, we have the vegetation height and GPP data. It's also 30 meter because Landsat is 30 meter. Landsat again is the most fundamental Earth observation data source for humanity, you know, and luckily U.S. government decided to make it open so we can all use it. So that's the 30 meter. We would like to move to 10 meter, have no doubts, but it's a really different level. I don't even know if we could build global mosaics at 10 meter. So that will be a really different level. It's about 10 times bigger every layer when going from 30 meter to 10 meter. Then you can aggregate, you know, if you don't like 10 meter, if you prefer 1 kilometer or 250 meter, you can aggregate. So that's another thing you can do. I mean, if people get a better accuracy at coarse resolutions, you know, we have the DTM variables we have at 6 scales, so we call them Gaussian pyramids. So you have 30, 60, 120, 240, 460, 480, sorry, 960. So you have a 6 scales, and any scale that, you know, you get a better accuracy, we say use it, you know. So we don't fix on a scale, you know. We want to have the best possible data and best possible accuracy and whatever helps us. There's a question about Mongolia. Mongolia willing to produce soil database. The data is time and space fragmented. What would you recommend us? Where to start? How can we collaborate? So there is in the paper that we wrote in the discussion, we write how to collaborate between national and global or continental projects. We have the same problem in Europe. You know, we have a global predictions and national. So there is a way to collaborate, and that is to combine the predictions to make ensemble out of global and local. Another option is to use a global predictions as an input to local, so just an addition. So there's a ways to do it elegantly. As long as everybody uses the same standard, it can be through different data fusion frameworks. The data can be seamlessly combined. So you're not really, you know, the worst type of data fusion is where you have two sources and they tell completely different story. But we notice in Europe that there is really a big match, you know, 80% is a match where they do global models and local. But local models will be more accurate because you have a more covariate data. So like when you do, you know, in Europe, we have a lithology map of Europe. We have now peatland map of Europe. And we have these detail layers, which we don't have for the world. So you will get for Europe locally better accuracy. But possibly some component of global model can help also local models. So definitely just send me an email. Mandak, please send me an email from Mongolia if you want to contribute or collaborate. We're happy to help you. We can provide you access to this data, including the covariate layers, and also help you, point you to the methods to use to produce the similar type of outputs. So organic carbon affected by different variables such as elevation, temperature. Have you seen this? I'm not sure about this question. I will skip it. Rafael has a question. So yeah, we have the soil organic carbon is integers. Integers is a gram per kilogram. This is so-called per mil. So gram per kilogram, 1 in 1,000. That's why you can save it as integer. But if you want to round it, for example, if you want percent, you divide by 10. That gives you percent. We need to save as integers because the cost of float, if you can believe, when you're in a big data, you have a big data problems. So just to have a GeoTIFF in floats, it's about 2 times higher storage if you don't round the numbers. But if you round the numbers, then cost you computing. So it's really simple things, you know, when you're with big data, but it can double the cost of storage. So that's why we use only integers. Because TIFFs, you know, they are not. It's possible to put floats, but the compression gets more complicated and everything. Is the training data for your model available somewhere to download? Anonymous attendee. Yes, the data is available, and you can also just load it. If you look at the book, so it shows you how you can access this training data. You can load it, and you can go ahead and also make your own global soil data, soil predictions. We don't want to, monopolize this or anything. We want to build a community for global soil mapping. There is an issue with the data, is that some data sets we're not allowed to share. And so I'm talking, for example, Lucas. As you know, Lucas is a fantastic data set. It's European and US data dominate the global modeling. So Lucas is a fantastic data, but it is available only for internal use. So we are also not allowed to share it publicly. So you have to add some data sets to this repository that we made. And we have a little questionnaire for you also. I will stop now with answering your questions. Thank you so much for questions. Thank you for joining, by the way. So we do have some questions for you. So please, just before we stop this webinar, if you could just go and give us an answer. There's only 5 questions. It shouldn't take you too much time. And you can also write any text you would like to write to help us improve this. I will leave this for a couple of minutes to run. And Bernd, yes, I also pass it to you. If you have some last closing words.
No, thank you very much. To those who joined us a bit late, we'll make the recording available so then you can see the first minutes in case you missed them. Thank you once more to Tom. I think it's also interesting to see the scientific proof for the direct link between GVP and the SOC, because that was the hypothesis which the current reporting for SDG 1531 and the use of the soil organic carbon sub-indicator is built. So it's good to see that recommended. One last question maybe to you. If countries want to use the data in the coming reporting cycle, I know that the data is in the carbon content at the moment. What's your advice for those countries if they want to use it in the upcoming UNCCD reporting cycle?
So if you don't have a national data or some like comparable data, you can use this global data. I do recommend it, especially this is dynamic data. Some countries, they have a static data, so you don't know what really is the change in carbon. But we have a really data strictly referenced to time, and we have more than 70% of covariate layers a time series. So we know exactly at the time that people did a soil sampling, we know what was the climate, what was the land cover, what was the GPP, what was the water vapor, etc. So they're really strictly temporally referenced, and I know that many countries don't have that. So if you don't have anything else, please use this. If you do have a national data, you can consider doing a data fusion. That could help you fill in the gaps. Some countries have only, for example, agricultural land. We have both agriculture, forest land, mangroves, all the landscapes. The only thing we don't map is the Sahara and deserts. We don't think there's a point in mapping that because it's very extreme climate places, and you can just put a single number. For example, you could put soil organic carbon is 0. There's no need to map that, I think. So that's what I recommend to people that want to access and use.
Excellent. Thank you once more. I think there have been 1 or 2 unanswered questions. We'll try to get an answer to you. Final thank you.
Let's leave this running for just 1 more minute because I see people are writing still.
Okay.
So, but it's
Sure.
very useful for us to get
definitely. We'll keep the survey open. Also, as I said, we'll send some additional information to participants, like a collection of the links shared in the chat here, and also a link to the recording once we have it up.
Somebody had an urgent need to say something. I see one.
Yeah, Manda from Mongolia had a follow-up. I think she wanted to know the number of in situ points used for the territory of Mongolia.
Okay, it's possible if you access the geo package on Zenodo, you can see how many points are in Mongolia. I don't think there are many. We have huge gaps, from big territory, so it's not ideal thing, and it is a very complex soil mapping. It remains very complex, and I was very naive. I did a PhD in 2003 in pedometric mapping, so I thought also in 2010, yeah, we're going to make now 100-meter resolution data for the world, and it took 15 years. Imagine, only 15 years after now we have it. Now I can say, yeah, it's done. Now we have the, and it is we didn't know what's going to come out. It was very exciting to see these maps in the end. I kind of knew what are the main patterns, but you never know until you really make the maps what comes out. And so it was interesting to see this GPP, because you have in LDN also GPP, right? You have it
exactly. Yeah.
So it's interesting to see how these things are actually, how you knew also in LDN, somehow you knew that these things are actually connected, because I think fertility, productivity, water, water fluxes. I mean, this is all really highly connected and systematic. And biodiversity also, they say FAPAR is a measure. FAPAR is also connected with GPP. It's a measure of biodiversity. So nature is not so, some things is not so complicated. You want to improve the health of the planet, increase the soil organic carbon, increase the GPP, and then you will have also higher biodiversity. Protect areas, protect tropical forest. We should protect maybe 60% of planet, I think. Not now, we protect what, 15% maybe,
and we're trying to go to 30.
So it's actually, some things is very simple. Some value systems, they're very simple. That we made them too complicated, I think. But now we have a scientific proof that things are also with soil carbon. It is relatively simple. Cut down deforestation, improve the GPP, convert land to perennial, so agroforestry systems, grasslands, decrease the tillage drastically, decrease leaving the soil bare over the longer period. And that helps then increase soil carbon and soil biodiversity.
Yeah, no, thank you, Tom. I mean, I think it's hard to appreciate enough the work you have put into this project over the last 15 years. As you said, it's much harder than one could imagine.
Luckily, it happened before I retired. It happened before I retired, so I was lucky, because I guess some professions, you work all your life and like, I don't know, some people want to land on the moon, but now it's been almost 50 years. We cannot land on the moon anymore. But so luckily I managed to get this, and now it will just get better. So we are getting more data. We just got data from China. We're very happy the Chinese group published point data and made them available. There's also Lehman Soda project published 2,000 locations. So there's a more point data coming, and we can integrate that and rerun it, and we do this reanalysis. The maps will get better and better. I mean, we will reach some plateau. You cannot make magic, Soils are hidden, soils are, we don't have any sensor. I mean, unless you do some gamma radiometrics or something, but there's no way that you can, like with the above ground, you can see an image of a leaf and reflection of a leaf of vegetation. With the soils are buried, they're hidden, and they still carry a lot of complexity, and there's a lot of past processes that you don't know, you don't see them. There's a glacier processes, some landslides happen in the past, or some overfloods, and you don't see them. So there's a lot of hidden things, and so they will stay difficult to map. That stays. But we made a little progress here. I think this is a little step forward.
Definitely. I don't know if Brian O'Connor from the UNCCD participated today. I may organize a short follow-up meeting with you and him in case you're available. So that is really interesting, I think, also for the UNCCD. Yeah, thank you to all those also who answered the questionnaire Still an answer coming in. Yeah.
I think I will stop now. I see people are
Yeah.
not writing anymore. I will stop.
Yeah.
I will share the results with you.
Excellent.
Yeah.
And thank you to all of you who...
Yes.
Go ahead.
Thanks to all the participants. Thanks for your questions and for kind words.
Wonderful. Okay. Yeah, and most people stayed with us until the end. Thank you so much.